center, timer, table of results, kettle, go in there, 22 degrees in the water, just go down, and then wait. So, specific heat capacity and latent heat. If you've done specific heat capacity before, it is a GCSE concept. Even if you've not, look at how easy that equation is. It's got 4 things in it: an E, an M, a C, and a delta theta, which you're welcome to call delta T. It is as easy as the 4-letter equation suggests. It tells you that the energy required to change the temperature of a given mass of some substance by an amount delta T is that. It depends on a material property because all different materials heat up at different rates, and that material property is the C in this equation. It's called specific heat capacity. Measured in joules per kilogram per Kelvin, it's the amount of energy required to raise the temperature of a unit mass of substance by 1 degree, or, as the definition says in the book, by 1 Kelvin. You'll learn about Kelvin in the next book, just write it down for now. 1 degree, 1 Kelvin is essentially the same at the moment. That equation is really, really easy to use. You just have to remember that delta theta, we see that symbol delta when we mean change. Delta theta is the change in temperature, not the actual absolute temperature of that thing. So for example, I can start heating something at 20 to 50 degrees. My delta theta will be 30 degrees. Let's think about that one for a second there. It's dead easy, and it works for cooling as well, because conservation of energy, the energy that you put in to heat something up is the same as the energy you get out when it cools down. So if something was cooling from 80 degrees to 50 degrees, my delta theta would be 30 degrees. Sometimes in questions you are given the change in temperature, and so you just use it outright. You know, how much energy do I need to raise the temperature of water by 25 degrees? You put 25 into the equation. But just be aware that you might just have to work out the difference. That's not beyond you guys. It is so easy. Try some of the questions. I guess the only other thing that I want to say about specific heat capacity is that that E could come from anywhere. You could expect to be doing an electricity calculation. Maybe you've got an electric heater. In fact, here's a question that I wrote earlier about an electric heater providing the energy in order to heat up a metal. This kind of crossover should be expected, and you'll see in the questions that E, it could be a half mv squared, it could be mgh, it could be P equals IV and time, it could be from literally any other energy that you are aware of. So keep that in the back of your mind. Look at the numbers that you're given. Do they fit into an equation? If not, what's the intermediate step? You know, I don't even really need to go through it, but just keep it on the back of your mind. I have literally nothing else to say about specific heat capacity other than you saw me at the start of the video playing with my kettle. I wrote up that results table, I put it in Excel and I plotted a graph, and you'll notice that it's a straight line. My kettle has a constant amount of energy being supplied per unit time. If I plot the amount of energy or time on the x-axis and the temperature of the substance on the y-axis, I get a lovely straight line. This means that the gradient has to incorporate not just specific heat capacity, but mass as well. And I'm going to do that magic thing where I rearrange the equation text-wise. And you can see that the gradient of this graph is actually inversely proportional to specific heat capacity. So the larger the specific heat capacity, the more shallow the gradient. And I think that's fairly obvious because if you think about it, if you have a large specific heat capacity, it will take a long time to heat up, and so that change in X is going to be long. If you have a small specific heat capacity, it won't take very long to heat up, so you have a small change in X. I think that's fairly easy to understand. Remember that you can just fact check yourself on that and think about it in an exam as well. Best just to learn it outright though. And that works right up until I hit the boiling point. Or if I'm cooling it down, right down until I hit the melting point. At the boiling point and the melting point, it's not the same gradient straight line, it actually flattens off. I think I can change my data here and I can just add on. So I held down the button on the kettle and I kept it trying to boil, and the temperature stopped going up. This would happen regardless of how I heated it, whether I had a Bunsen burner, and ideally I would do, but I'm not in my lab, or whether I had a heat plate, or whether it was in a fire or a furnace. It would eventually stop at 100 degrees. What is going on there? So the next part of this book concerns a change in state, and I'm actually going to skip over the first bit, and I want to talk about this graph. I'd really hoped to do this, but when I experimented with putting some icy water in my kettle, I found that the time it took to melt was massive compared to the time it took to heat up. But you're welcome to try it. So if I were to put some icy water or some ice in my kettle at a temperature lower than 0, so for example if I took it out of the freezer at -5 and I turn the kettle on, you'll notice that you can see the ice heating up, but then it goes flat for a while. What you'd observe in there is that the ice was melting. When that ice had melted, you'd see the temperature start to rise again. It probably wouldn't be as perfect as this graph in practice, but it would be pretty clear, trust me. I've done it for about 5 years in lessons. That temperature starts rising again, and you get that lovely straight line as the water heats up. And then it flatlines again. And in lesson, I can't actually run the experiment for long enough for that flat line to stop. The next flat line is much larger, and that's where it's vaporizing. And I don't know whether you've ever tried to boil away a full amount of water. You know, if you put a bit of water in a pan, it takes a long time to boil away that water and completely evaporate it. So the top line is where the liquid is evaporating, and it will sit at 100 degrees there on the boiling point for quite a long time. But if you could trap all of that gas, once it is all evaporated, it then just continues moving up with a beautiful straight line. This graph tells us everything that we need to know about what happens to a substance when we take it from being a cold solid and we raise its temperature to being a hot gas. Every state has a specific heat capacity, and every state's specific heat capacity is different. So you might notice that the gradient of a line for ice is different to the gradient of a line for water, is different to the gradient of a line for a gas. Why don't you Google specific heat capacity for water, ice and steam? It'll be the first thing that comes up, and compare those values. You'll find that liquid water has the highest specific heat capacity by a factor of about 2 at 4,200 joules per kilogram per Kelvin. So what are the flat areas? Well, when an object changes state, it requires a specific amount of energy as well. Obviously, it depends on the mass that you've got, and so this is called a specific latent heat. When we're trying to melt or indeed freeze, this works both ways, a substance, we require a specific amount of energy per unit mass, and that is called the specific latent heat of fusion. Thermal energy required per unit mass to undergo the solid to liquid phase change, or the liquid to solid phase change. It's important, just a little thing to remember, that latent heat of fusion, it goes both ways whether you're trying to melt or freeze something. It's a conservation of energy. That same amount of energy has to come out as goes back in. Likewise with vaporization, you require a specific amount of energy per unit mass to change the state of water from a liquid to a gas. And that works both ways around as well. The equation, if you thought specific heat capacity was easy, is even easier. It's E equals mL. I mean, what more can I say? thing to remember is that there is no change in temperature while you're changing state. That is not a simplification, it is what actually happens. And if you don't believe me, get some ice, get a temperature probe and heat it up, maybe in a safe environment over the kitchen hob or put it in the oven. You will see that regardless of what happens in the environment around it, the temperature of that ice will remain at 0 degrees while it melts, and the temperature of the water will remain at 100 degrees whilst it boils. There's another little standard answer there looking back to internal energy. Remember that internal energy is the sum of the randomly distributed kinetic and potential energies of the particles. And what we see here is that difference between the two. When we change the temperature of a substance, its kinetic energy increases. But when we change the state of a substance, it's the potential energy that increases. And we see that almost absolute dependence of kinetic energy on temperature. That's essential later on in the ideal gas booklet as well. Again, kinetic energy is entirely to do with temperature, potential energy is entirely to do with the state and state change. So to finish off, I know that I said that the equations are easy, and they are, they're dead easy, and a lot of the time you can get 3 easy marks for putting numbers into those equations and you will love them. But examiners know this. It is possible for questions like this to get pretty complex. Example 3 in the book is a great example of a more complex question where we have to consider more than just one little bit of that temperature change and state change. In example 3, you're looking at the energy required to range the temperature of a mass from 25 degrees to 120. It's not told you that it's changed state, but it has given you the specific heat capacities, and they will always give you specific heat capacities, by the way. Look for that data. And it's a bit of a clue that they've included the specific latent heat there. That should be a clue that that's required. Now I know if I took an untrained GCSE physicist, they would probably be able to do it, but it would be an absolute mess. You are one of my well-trained A-level physicists, and you know that I care how working is laid out. So think about what has to happen here. You've got to heat up the water, then that water's got to boil entirely into steam, and then you've got to heat up that steam. So take the time to split your page into those 3 steps. However you want to do it, here, here and here, or down the page as it's done in the book. Notice how it's laid out. That will help you. I wish that I could show you examples of student work where they've not laid it out properly and they've got it wrong and they're confused, and then other students who've laid it out properly but still made a mistake somewhere and can see exactly what the problem is and fix it straight away. It really makes a difference. So as you can see, we can work out each section individually and then we just add them up. I'll give you a slightly different example of where you might also be careful. So let's say you've got a drink of water and you put an ice cube in it. What's going to happen to the temperature of the water? It's going to go down, Rob. That's why I use ice cubes. You are correct. So when you do your calculation, would you accept an answer when it goes up? Sometimes forget common sense when they're doing these questions. Heat flow matters, and that's why at the start of the book it mentions thermal equilibrium. Heat always flows from a hotter object to a colder object. So sometimes you have to consider, what is the source of your energy? In the case of the glass and the ice cube, the water will be providing energy to the ice cube, heating it up, or rather just melting it. You would need to find out how much energy was required to melt the ice cube, and then find out what change in temperature that caused the water to undergo. It could suddenly become quite a complicated question. If there's a significant amount of ice, you might also need to calculate how much that water at 0 degrees when it melts requires to heat all the way up to the final temperature of the water. To boot, in a question like this, the masses that you're going to use in each side of the equation are different. People countless times will get those masses mixed up, and you have to be careful. The mass that's melting is the ice cube mass. The mass that's cooling down is the water mass. And you need to just be careful that you're using the right mass in the right place. What's best is to go and practice. Don't just jump right in at the end if you've seen this before, maybe in the middle. If you want to build your confidence and you've not used specific heat or latent heat before, start at the beginning, work your way through those questions. And if you have any questions, just let me know. I'm not that busy, although I am going in college a little bit more now. I want you to get in touch. That's all. If you can do this little plenary, then you've got it. I'll see you next week.